65th lecture on circuit analysis. We will continue studying power in three-phase systems, and we will, in this lecture, we will continue studying power in three-phase systems. In last lecture, CA64, we studied expressions, different expressions for total and per phase powers in a three-phase system. Right. In this lecture, we will solve a numerical example. We are given our delta connected system. In fact, our delta connected load, where the per phase impedance is C delta, and the line voltage between A and B terminals is 208 at an angle of 0 volts. And of course, this is VL, and we know that in a delta connected load, we only have the line voltage, whereas we have two sets of currents, the line current and the phase current. And we know that phase current is line current divided by square root of 3 in a delta connected load. Right. So let's move on. We are also given the total power in all three phases is 1200, 1200 watt, and the load is 0.93 lagging in each phase. The load is 0.93 lagging. Right. So we will have to find the line current that we can also represent as IA, the line current, and this C delta, this one, or this one, or this one. So the impedance is the same in all three phases. So we have to find the impedance of one of the three phases, C delta. Right. Let's tackle this problem using the expression that we studied in last lecture 64. We studied the total power in a three-phase system, no matter either it is a Y-connected system or it's a delta connected system. No matter, the expression remains the same. That is under root 3 times line voltage times line current times cosecant of theta, that is the power factor. We know that cosecant of theta is power factor. We have studied it earlier. So let's plug the values that are given. The total power, the line voltage 208, its magnitude, it's given, and we are given that the power factor is 0.93 lagging. So we'll put 0.93 here. So we have only one unknown in this equation. So we'll solve, and the magnitude of IL, the load current, comes out to be 3.58. Right. So we have computed one of the unknowns, the magnitude of the line current or the magnitude of IA. So it's all magnitude of all line currents is the same, no matter if it is IP or IC. Right. So the next thing that we were asked to compute was the per phase impedance C delta. Right. So let's consider this C delta. We know the voltage across it is VAB, which is a line voltage, and the current through is IAB, that is the phase current. So in fact, Z delta, the magnitude of Z delta is the line voltage divided by the phase current. The line voltage divided by the phase current. So if you want to compute the magnitude of Z delta, we'll divide line current divided by the phase voltage, VL divided by IP. And we know that phase current is in delta connected system. We have two sets of currents, the line currents and the phase currents. And we know that phase current is the line current divided by square root of 3. So when we'll plug this value, it comes out to be, and we know VL, we know IL, we have computed IL, we are given VL. So everything is known except Z delta. So Z delta comes out to be 101 ohms. The magnitude comes out to be 101 ohms. So what should be the power factor of this? What should be the angle of this Z delta? We know that C delta, the angle of C delta is the inverse of the power factor, inverse of the power factor. We know why is it inverse? Because cos inverse of the power factor, which gives us cos inverse of theta b minus theta I, and we know that theta b is 0. It's given to be 0 at an angle of 0. So the angle of current would be inverse cos inverse cosecant of the power factor, that is 20 degrees. So the angle of current is 20 degrees. This means the angle of this impedance is also 20 degrees, because the angle of voltage is 0. So Z delta is 101 at an angle of 20 degrees, and it shows that it's ohms, and it shows that it is a lagging impedance. It's an inductive load causing a lagging power factor. It's an inductive load. How do you know that it is an inductive load? Because if we convert this polar number into a rectangular number, this this will have a real part, which is always positive, and a positive imaginary part. Because how do we know that it will have a positive imaginary part? Because the angle is positive. So if we have a negative angle here, the imaginary, when we convert it into the rectangular form, the imaginary part would be negative. This means a capacitive load. Since we have a positive angle, this means a positive imaginary part, and it is an inductive load. And we know that for inductive loads, we have lagging power factor. And we know that for capacitive loads, we have leading power factors. Right, we'll continue studying more about three-phase power in our upcoming lectures. Thank you.